Okay, so hi everyone, I am Shivani Dhok, and today we'll be looking at the week 4 tutorial session and content of whatever was covered in the week 4. So let us start with it, and I also hope that my screen is visible to everyone. So in week 4, the concepts that were covered was based on or related to Laplace transform. So a quick recap of what a Laplace transform is. So if I am having x of t as a signal, then it will have its Laplace transform x of s with a region of convergence, that is ROC, and this x of s is obtained using the formula integral minus infinity to infinity x of t e power minus st dt. So this is the formula for your Laplace transform. Now along with this, there were several properties of Laplace transform that were discussed in this week 4. So the first property that was discussed was linearity property. So suppose there are two signals x1 of t and x2 of t, and x1 of t has its Laplace transform as x1 of s, and x2 of t has its Laplace transform as x2 of s, and this has ROC R1, this has ROC R2. So this linearity property says that if I consider a linear combination of these two signals, that is a times x1 of t plus b times x2 of t, then its Laplace transform will be a times x1 of s plus b times x2 of s, and the ROC will be R1 intersection R2. Similarly, there were several other properties. So the next one was time shifting property. That is, if I shift a signal x by some factor t naught, then its Laplace transform will be scaled by this factor e power minus s t naught into x of s. There will be no change in ROC. Then if I have a shift in Laplace domain, that is if I have something like this, x of s minus s naught, then in the time domain I'll be having this factor, something like this. Then there was differentiation in time, that is if I take dxt by dt, then its Laplace transform will be simply s times x of s. Then there was differentiation in s, so it was something like this. If I have a signal t into x of t, then its Laplace transform will be minus of d ds of x of s. And the next one was integration in time, that is if I consider integration of my input signal, then my output will be, or rather the Laplace transform of this signal will be s times x of s. And the last property that was covered was convolution in time, and it says that if I have two signals x1 of t and x2 of t, so I'm just convolving these two signals, then at that time my output will be x1 of s into x2 of s. After that, the concept of poles and zeros was discussed. So what it was said that my Laplace transform is generally of the form numerator polynomial upon denominator polynomial, something like this, and the roots of numerator are known as zeros. So its roots are zeros, and the roots of denominator polynomial are poles. Another thing that was discussed was properties of region of convergence. So it was said that if I have a right hand sided signal, then my ROC will be right to the maximum real part of the maximum real part of the pole. That is, if my signal is right handed, then in that case my ROC will be something like this: real part of S greater than or equal to sigma max. And if it is left handed, if the signal is left hand sided, then my ROC will be of the form real part of S less than sigma min. Then the inverse Laplace transform was also discussed, and there were some simple techniques that were used to find the inverse Laplace transform. After that, the Laplace transform for LTI systems was discussed. So basically the concept is something like this. So if I have an LTI system with impulse response h of t, and if I give an input as x of t and I observe an output y of t, then this output is simply convolution of x of t with h of t. And if I use the convolution time convolution property of Laplace transform, then this can be simply written as y of s is equal to h of s multiplied by x of s. Okay. And using this, I can find h of s as y of s upon x of s, and this h of s is known as the transfer function of the system. Now, the region of convergence of this transfer function has something to do with causality and stability. So if a system is causal, then my h of t is 0 for all t less than 0. This means that my signal is right hand sided. Which means that if my signal is right hand sided, my ROC will look something like this. And then ROC of a causal system will always be in this form. That is, it will always be towards right. That is, it will satisfy a situation or an equation something like this. For stability, this region of convergence should include the j omega axis. This axis j omega should be included, this axis should be included for the region of convergence of a stable system. So these were the concepts that were covered in the week 4, and based on these, let us try to solve some questions. And in last week I covered two simple questions which used mostly the Laplace transform basic definition. In this week, okay, so there is a question which is asking what is a double-sided signal. So double-sided signal means something like this. If I have a signal e power minus mod at, and suppose my a is greater than 0, then this signal looks something like this. Now it is all right hand sided, also it is left hand sided, which means it is double sided. It is extending from minus infinity to infinity. I hope that clears it. So in this week we'll use the basic definition of Laplace transform, along with we'll try to use the properties of Laplace transform, and we'll see that these properties help us a lot in simplifying or in finding the output or in finding the Laplace transform of the related signals. So for that, let us take one simple example. That is, suppose I have this signal xnt, which is given as t power n xt, and let's say this x of t has a Laplace transform x of s. So the information that we have is this x of t is having a Laplace transform x of s. Now let's say its ROC is given by some region R. We don't care about it, whatever be the ROC, because multiplication by this t won't be changing my region of convergence. So now suppose my region of convergence is R here, and my xn of t is given something like this, t power n xt. So now if we look at this property here, so what do we have? T into x of t has a Laplace transform of minus dds of x of s. So we'll try to use the property differentiation in Laplace domain or in S domain, and the property says that t into x of t has a Laplace transform of minus of dds of x of s. That is differentiation of Laplace transform in the Laplace domain with respect to s. Now this we have. Now suppose I consider the Laplace transform of t into t times x of t, that is, so this is nothing but t square x of t. So its Laplace transform will be differentiation of this, that is, I'll have a negative sign here, and dds of minus of dds of x of s, and this comes out to be minus 1 to the power 2 dds or d2 by ds square x of s. Similarly, if I take t cube x of t, then this will have a Laplace transform of minus of dds of minus 1 power 2 d2 by ds square x of s, and this is equal to minus 1 power cube d3 by ds cube x of s. So if I just extend it and see the pattern, I can simply write that t power n x of t has a Laplace transform of minus 1 power n dn ds power n x of s. So this is the Laplace transform for my signal xn of t. And now I'll use this property to solve the next part of the question, that is, if x of t is e power minus 2t ut, we need to find the Laplace transform of x2 of t. So what do we have is the x of t is now given as e power minus 2t u of t, and we need to find the Laplace transform of x2 of t, and this is simply t square x of t. So let us first find the Laplace transform of this function. So let's say x of s is Laplace transform of x of t, so we can find it as minus infinity to infinity e power minus 2t ut e power minus st dt. This is equal to minus infinity, or rather we'll use the definition of unit step function, that is, it will be non-zero from 0 to infinity e power minus s plus 2 t dt. This is simply minus e power minus s plus 2 t upon s plus 2, ranging from 0 to infinity, and this is equal to 1 upon s plus 2, and at infinity this will tend to 0 only if real part of s is greater than minus 2. So if that is the case, then only this x of s will be converging. So this is the Laplace transform that I am getting for x of t. Now we don't need the Laplace transform of x of t. What we need to find is the Laplace transform of this signal, that is x2 of t, which is given something like this. So if I use the expression that I have derived here, so the Laplace transform of this signal x2 of t is simply, let's say, x2 of s, which will be equal to minus 1 power 2 d square by ds square x of s. So this is equal to d2 by ds square x of s. Now let us try to find this. So for that, d ds of x of s is equal to minus 1 upon s plus 2 square, and then d ds d2 by ds square of x of s will be differentiation of this function, which will be simply equal to minus 1 into minus 2, that is 2 upon s plus 2 cube, and this operation will not change my region of convergence. This region of convergence will remain real part of s greater than minus 2. So if we draw this region of convergence, it will be simply like this. I have minus 2 here, and I have a pole at minus 2. It can be observed here. I have 3 poles. I have 3 poles at s equal to minus 2, and this is how we indicate a pole. And my region of convergence is everything that is greater than minus 2. That is real part of s greater than minus 2. This is my real part of s. This is equal to sigma, and this is my imaginary part of s with a j sign, that is j omega. Now, how this property is helping us, how this differentiation property is helping us is this signal. This signal is a very well known signal, and the Laplace transform of this is actually known, and it should be known so that we can find the inverse Laplace transform. So this, any signal which is of the form e power minus at ut and e power, or rather minus of e power minus at u of minus t, these are some standard signals. Also the cos omega t ut, sin omega t ut, these are very common signals, and the Laplace transform of these signals are well known. So if I am having a well known signal which is something like an exponential in this case, now again repeating the entire process of finding Laplace transform using this equation becomes a tedious job. Instead, I am having a simple trick that I can just differentiate the function, this simple 1 by s plus 2 function, and find the Laplace transform without integration and other stuff. So that's why this approach, or knowing the properties, help us in reducing the complexity that is involved in this computation of integral. It makes our job quite simple. That's why use of properties, or that's why we analyze the properties to make our life simple. So this is all about this question. If there are any questions, please let me know. If there are any doubts regarding this entire thing, please let me know. Let us look at the next question. In the tutorial, or rather in the week's session, the Laplace transform of cos of omega t was found, and Laplace transform of cos of omega naught t ut, this was obtained as s upon s square plus omega naught square with a region of convergence of real part of s greater than 0. This was obtained in the tutorial. Now let us look at Laplace transform of a sine function. This is also a standard function. It is good to know what this yields to. So let us look at this. So what I am having is x1 of t is equal to sine omega naught t u of t. Now let us use x1 of s is equal to integral from minus infinity to infinity sine omega naught t ut d into e power minus st ut dt. This I can write as, or rather I don't need this ut. This sine of omega naught t I can write as in terms of complex exponential, something like this. And also I can just use this definition of u of t and change the integral limits from 0 to infinity. And sine of t I'll simply write as e power j omega naught t minus e power minus j omega naught t upon 2j multiplied by e power minus st dt. This I can separate in two separate integrals, 1 upon 2j integral from 0 to infinity. I can combine this and this term, this one and this one. So I can write it as e power minus s minus j omega naught t dt plus, or let's say minus 1 upon 2j integral from 0 to infinity e power minus s plus j omega naught t dt. The first integral gives me a result as 1 upon 2j e power minus s minus j omega naught t upon minus of s minus j omega naught 0 to infinity minus 1 by 2j e power minus s plus j omega naught t upon minus of s plus j omega naught from 0 to infinity. Now the first thing, this one at t tending to infinity will lead to 0 only when my real part of s is 0. So this will lead to 1 upon 2j 1 upon s minus j omega naught, and this will happen when my real part of s is greater than 0 minus 1 upon s plus j omega naught. Similarly, this will happen, that is the second integral will converge, that is this e power minus s plus j omega naught t will converge to 0 or will lead to 0 only when my real part of s is greater than 0. So this will lead to 1 upon 2j omega naught upon s square plus omega naught square, and this is equal to omega naught upon s square plus omega naught square, and real part of s greater than 0 is my region of convergence. Now let us look at the poles of this. So poles are simply roots of the denominator. So s square will be equal to minus of omega naught square, which means that s equal to plus minus j times omega naught are the poles of this equation. And if I draw the region of convergence, it will be something like this. I have a pole at j omega naught. I have a pole here that is minus j omega naught, and my region of convergence is everything that is right to real part of s greater than 0. So this is sigma. this is j omega naught. So this is the Laplace transform of x of t equal to sine omega naught t ut. Any questions at this point? Okay, let's look at the next part of the same question. Now let us say that I am not considering the sign only for positive value of t. Let us say that we are taking a sign from minus infinity to infinity. So this x2 of t is equal to sine of omega naught t, and I can write it as sine of omega naught t u of t plus sine of omega naught t u of minus t. Is this step clear with everyone? Okay. So now if I consider this part, this is simply our x1 of t. So this I can write as x1 of t plus x2 of t tilde. Let's say it is x2 of t tilde. Now we have already found the value of x1 of t, and the Laplace transform of this we have found in the previous part. Now let us just focus on this x2 of t. So let's say it has a Laplace transform x2 tilde of s, and it can be calculated as minus infinity to infinity, but I have a u of minus t here, so that will just extend from minus infinity to 0. So I can keep it something like this, and then I can write this sine of omega naught t. Again I'll use the same substitution here, that is e power j omega naught t minus e power minus j omega naught t by 2j into e power minus st dt. Same steps will have to repeat, but the integration limits are now different. So this is from minus infinity to 0, e power minus s minus j omega naught t minus e power minus s plus j omega naught t upon 2j dt. This will lead to 1 by 2j e power minus s minus j omega naught t upon minus of s minus j omega naught from minus infinity to 0 plus 1 by 2j, minus 1 by 2j integral e power minus s plus j omega naught t upon minus of s plus j omega naught from minus infinity to 0. Now this exponential, when my t is tending to minus infinity, will lead to 0 only when my real part of s is less than 0. So this will be equal to minus 1 by 2j into 1 upon s minus j omega naught, only when this will converge only when my real part of s is less than 0. Similarly, this will converge to 0 when t is tending to minus infinity only when my real part of s is less than 0. So this will be equal to 1 upon s plus j omega naught only when my real part of s is less than 0. Now if we look at the region of convergence of this x1 tilde. So my x1 tilde was having a region of convergence something like this. this region of convergence was for x1 of t, I'm sorry, not x1 tilde, x1 of t, and for this signal x2 of t tilde, my region of convergence is coming something like this. So this is my region of convergence for x2 tilde. But when I am applying linearity property, the region of convergence for this x2 of t should be intersection of these two region of convergence, which is not at all happening here. So in that case, if my region of convergence are not at all overlapping or not at all intersecting, that is my ROC is equal to null set, that is phi, which means that the Laplace transform does not exist. Is this question okay? No, they are not converging at 0 because you at 0 you are having a pole. So there is a question that let me read it once. Yeah. So the question is, are they converging at 0? So no, the Laplace transforms are not converging at 0 because at 0 you will be having a pole. I'm sorry, at 0 you won't be having a pole, but that entire 0 axis is not included in your ROC. That is, here your region of convergence is less than 0, and in for this x1 of t your region of convergence is greater than 0. So in both the region of convergence your 0 is not at all included. So it is not in the region of convergence, so it is not converging. Is it clear? Region can be a points, but for this question, let me draw that properly. Okay. Okay, this is your real part of S. This is your imaginary part of S, or let's say j omega naught omega, and this is your sigma. That is my S is sigma plus j omega. Now for your x1 of t, what was your region of convergence? It was something like this. So this is the region where my real part of S is greater than 0. Is there any equality here? Your real part of S is not greater than or equal to 0. Your real part of S is less than 0. Means the line corresponding to real part of S equal to 0 not in ROC. So this is not included in ROC. Which means that this signal, this Laplace transform is not converging at s equal to 0. Similarly, if I consider the other signal x2 tilde, its region of convergence is something like this. This one is for x2 tilde and it says that it is real part of s which is less than 0. Again, real part of s equal to 0, not in ROC. And if I consider, let's say this is R2 and this is R1, and if I consider R1 intersection R2, it is a null set. And anyways, in both the ROCs, real part of S equal to 0 and real part of S equal to 0 are not included in R1 and R2. So by no chance it will be there in R1 intersection R2. So if it is not converging in both the cases, or if it is not converging in at least one of the xt, it won't its linear combination will not converge, and therefore at s equal to 0 it won't be converging. If that is clear, I'll move on to the next question then. So the next question that we are considering is this: we need to find the Laplace transform of xt equal to e power minus a mod t. So if I consider x of t is equal to e power minus mod at, so this is equal to e power at if my t is less than 0, and this is equal to e power minus at if my t is greater than or equal to 0. So I can write this as e power at u of minus t plus e power minus at u of t. So these are the two signals that we are having, and this is equal to your x of t. So what we'll do, we'll apply linearity property. So first we'll find Laplace transform of this, and then we'll find Laplace transform of this. Both of these are some standard signals, and therefore for once I'll derive the Laplace transform of these two again, so that we can use it for finding inverse in the coming questions. So let us first try to find the Laplace transform of this. So let's say this is x1 of t and this is my x2 of t. So the Laplace transform, let's say x1 of s is equal to integral minus infinity to infinity x1 of t e power minus s t dt. I know we can use the results directly instead of calculating it, but I want it to be calculated once so that it can be used for further questions. Like that is, I'm just trying to establish this result once again for better understanding of everyone. So this x1 of t can be written as minus infinity to 0 e power at e power minus st dt. This can be written as integral from minus infinity to 0 e power minus s minus a t dt. This is equal to e power minus s minus a t upon minus of s minus a from minus infinity to 0, and this will be equal to minus of 1 by s minus a. When will it be the case? When this exponential tends to 0 as my t tends to minus infinity, and that will be the case only when my real part of s is less than a. Next thing is Laplace transform of this x2 of t. So it is x2 of s, which is equal to, since it is e power minus at ut, I can write this u of t from 0 to infinity e power minus at e power minus st dt. This is equal to integral from 0 to infinity e power minus s plus at dt. This is equal to e power minus s plus a t upon minus of s plus a from 0 to infinity, and this is equal to 1 upon s plus a only when this is converging to 0 as my t is tending to infinity, and this will happen only when my real part of s is greater than minus a. Now let us try to find the Laplace transform of x of s. So x of s will be equal to x1 of s plus x2 of s. This is linearity property, and its ROC will be simply R1 intersection R2, that is region of convergence for x1 of t intersected with region of convergence for x2 of t. So x1 of s we have obtained as minus 1 by s minus a. So this is equal to minus 1 upon s minus a plus this we have obtained x2 of s is 1 upon s plus a. So this is equal to 1 upon s plus a. Now my r1 is equal to real part of s less than real part of s, yeah, less than a, and my r2 is equal to real part of s greater than minus a. So let us try to plot it. This is my sigma, this is j omega, then this is my minus a, this is my a. By, let's say I draw a line here and draw a line here. My r1 is the region where my real part of s is less than a, so it is this region. And this is my r1, red one, r1, and my r2 is real part of s greater than minus a, which is something like this. This is r2, and the region of convergence for x of s is simply the intersection, that is the overlapping part, which I am shading with this color. And this region, shaded one, is simply r1 intersection r2, which is region of convergence for x of t. And this I can write as this real part of s is less than a and is greater than minus. So this is the region of convergence for the case when my signal is something like this, that is something like this. So we can observe that for a double-sided signal I am having an ROC which is of the form of a strip, a vertical strip. Is this question okay? Okay, let's go ahead and try to solve this question. Now here what are we having? We are having this signal x1 of t. This x1 of t is given as e power minus at sine omega naught t u of t. In I think second question, first part, we have found the Laplace transform of sine omega naught t ut, which is something like this. So I'll just write it that sine omega naught t ut. So this signal has a Laplace transform as omega naught upon s square plus omega naught square, and its region of convergence is real part of s greater than 0. Now the signal that I am having is x1 of t, which is equal to e power minus at multiplied by this signal, that is sine of omega naught t ut. Now there is a property, that is shift in Laplace domain or in S domain, and it says that if I have something like this in my Laplace domain, so basically it is the Laplace transform of x of t into e power s naught t. Now this is the property which we are having here. Now if we observe carefully at this point, this signal x1 of t, this and this are having same format. So if we observe carefully, this is my s naught here, that is my s naught is equal to minus a, and if I use this property, then we can easily find the Laplace transform of this without finding explicitly using the integration expression. So here my s naught is minus a, and this is my x of t, and for this is my x of s. So if I consider this, that is x1 of s, using this property shift in s domain will be simply x of s minus s naught, that is x minus of minus a, which is equal to x of s plus a. Now this I can write as, using this equation here, omega naught upon s plus a square plus omega naught square. Now this thing is actually shifting in s domain, which means that my ROC will also get shifted by this same factor, and therefore that is this s minus s naught should belong to the region of convergence this of this one, that is real part of s greater than 0, which means that real part of s should now be greater than s naught, and here my s naught is a, which means that real part of s should be greater than minus a. And if I draw it, it will be something like this. Let's say my a is a positive number as it is given here, so it will lie something here, and my region of convergence will be something like this. Where will be the poles lying? So the poles are basically, my poles are nothing but roots of this polynomial. So what I have is s plus a square plus omega naught square equal to 0. So s plus a is plus minus j omega naught. So s equal to minus a plus minus j omega naught. These are the poles of this Laplace transform. And I can mark it something like this. So if it is my j omega naught, and this is my minus j omega naught. So this is the Laplace transform of this signal x1 of t e power minus at sine omega naught t ut. Now we'll try to find the Laplace transform of this signal, that is x2 of t equal to t into e power minus 2t sine 2t u of t. So what do we have is, we need to find the Laplace transform of x2 of t is equal to t into e power minus 2t sine of 2t into u of t. And what we have from the first part is, if I signal x1 of t is equal to e power minus at sine of omega naught t ut. If this is my given signal, then this has a Laplace transform x1 of s is equal to omega naught upon s plus a square plus omega naught square, and my region of convergence is real part of s greater than minus a. So this is what we had found in the previous part. Now in this equation, if I set my a equal to 2 and my omega naught equal to 2, then my x1 of t can be written as e power minus 2t sine 2t u of t, and this will be having its Laplace transform by simply substituting whatever values of omega naught and a we are having here. So this will be equal to 2 upon s plus a, that is s plus 2 square plus omega naught square, that is 2 square, which is 4, and the region of convergence will be real part of S is greater than minus 2. Now my x2 of t, the Laplace transform which we need to find, so this is equal to x2 of t is equal to t into x1 of t. And if I use the property differentiation in S domain, then the Laplace transform of this is simply minus of d ds of x1 of s, and this is equal to minus of d ds of 2 upon s plus 2 square plus 4. This is equal to minus of minus, so it will be simply plus 2 upon s plus 2 square plus 4 whole square multiplied by 2 into s plus 2. So this is the region of convergence, that this is the Laplace transform value that we are obtaining. So this I can simply write as x2 of s is equal to 4 into s plus 2 upon s plus 2 square plus 4 whole square, but my region of convergence won't be changing, so this is equal to real part of s greater than minus 2. So this is the Laplace transform of this given question. Any questions at this point? Okay, let's look at the next question then. So here we are given this signal x of t is equal to 1 for t which is from 0 to a, and it is 0 otherwise. So if I sketch this signal, it is something like this. This is my t axis, this is my x of t, this is 0 and this is a, and it takes a value of 1 from 0 to a, and then it is 0 otherwise. Now we can write this x of t as u of t minus u of t minus a. So what we have is x of t is equal to u of t minus u of t minus a. Now this is a standard signal, and the Laplace transform of this is 1 by s, which was covered in the week 3 lectures, and this is u of t minus a. So if I use the time shift property, so what does it say? If my x of t has a Laplace transform, and let's say x tilde of t has a Laplace transform as x tilde of s, then if I shift it, that is if I shift this by some factor t naught, then my Laplace transform will be scaled by a factor of minus s times t naught x tilde of s. So this is simply shifted by a factor a, so I'll get a factor of e power minus as upon s. Therefore the Laplace transform of this will be equal to 1 minus e power minus as by s. So this is the Laplace transform for x of t that we are getting. Now this is a finite duration signal. If it is a finite duration signal, its Laplace transform is the entire S-plane with possibility of poles at s equal to 0 or s equal to plus minus infinity. Now we can observe that here we will be having a pole at s equal to 0. So this is a pole. But my region of convergence is entire S-plane excluding this point S equal to 0, because based on the definition of your ROC, poles cannot be in your region of convergence, and therefore entire S-plane is your ROC with the fact that S equal to 0 is not included. I hope this is clear to everyone, and if it is, I'll move on to the next question. The next questions that I am going to cover are based on finding the inverse Laplace transform of the given Laplace transforms. That is, I'll find x of t for given x of s and region of convergence. But for that, I'll list down some standard Laplace transforms. So the first one is unit impulse. So this has a Laplace transform of 1, and this region of convergence is entire S-plane. The next one is unit step function. So this has a Laplace transform of 1 by s, and its region of convergence is real part of s greater than 0. The third one is the exponential, that is e power minus at ut, and this has a Laplace transform of 1 upon s plus a, and it has a region of convergence of real part of s greater than minus a. Fourth one is e power minus, or let's say minus times e power minus at u of minus t, and this has the Laplace transform of 1 upon s plus a, and its region of convergence is opposite thing, that is real part of s is less than minus a. The fifth one is sine omega naught t ut. This has a Laplace transform of omega naught upon s square plus omega naught square, and its region of convergence is simply real part of s greater than 0. And similarly, cos function, cos of omega naught t ut, has a Laplace transform of s upon s square plus omega naught square, and the region of convergence is simply real part of s greater than 0. So these are some of the standard Laplace transforms, and we will make use of these to solve the next few questions which are based on, or for which we are going to find the inverse Laplace transform. So let us look at the first question. So here we are given x of s something like this. So my x of s is equal to 1 upon s into s plus 1 into s plus 2 square, and we have to find x of t for three cases of ROC. The first one is real part of s greater than minus 1, the second one is the real part of s less than minus 2, and third one is the one where my real part of s lies between minus 2 and minus 1. So let us first try to find this x of s in a much simpler form so that we can use at least one of these things. So what we'll do is, so let us take this x of s, and this is equal to s into s plus 1 into s plus 2 square, and this I can try to represent using partial fractions. So this is c1 upon s plus c2 upon s plus 1 plus lambda 1 upon s plus 2 plus lambda 2 upon s plus 2 square. This factor here, lambda 1 and lambda 2 cases are arising because I'm having a repeated pole with multiplicity of 2 at 2. So these two correspond to this. Now there is one formula which is taken in the um normal lectures, but if that formula is little bit confusing, then instead I can simply go with very simple things, like I can simply cross multiply all of these terms so that I can get this in the denominator for everyone, and then what I can do is 1 upon s into s plus 1 into s plus 2 square, which will be equal to c1 into s plus 1 into s plus 2 square plus c2s into s plus 2 square plus lambda 1 into s plus 2 into s plus 1 plus lambda 2 I can write as lambda 2 into s plus 1. This whole thing is divided by s into s plus 1 into s plus 2 whole square. So this I can simply write as 1 equal to c into s plus 1 into s plus 2 square plus c2, so this is c1 into s plus 2 square plus lambda 1 into s plus 2 into s plus 1 plus lambda 2 into s plus 1. Now I need to find the values of c1, c2, lambda 1 and lambda 2. So let us first try to find the value of c1. Now if I observe carefully, there is no term of s here, but it is present here, here as well as here. So what I'll do, I'll just substitute s equal to 0. So if I do that, my equation becomes 1 equal to c1 into 0 plus 1, that is 1, and 0 plus 2 whole square, that is 2 square, which is equal to 4, and rest all the terms go to 0, which means that my c1 is equal to 1 by 4. We are doing the same thing that is taken in class, but this makes a little bit simpler thing. Next, I need to find the value of the c2. You can observe that s plus 1 term is not present here, but it is present everywhere else. So I can just kill it by setting s equal to minus 1. So if I do that, then my equation becomes 1 equal to, this term goes to 0, all the other terms go to 0. So this will be equal to c2 into minus 1 into 2 minus 1, 1 square, that which implies that my c2 comes out to be minus 1. Next I need to find the value of lambda 1 and lambda 2. Let us first try to find what is the value of lambda 2. This doesn't contain the term which is s plus 2, but other all terms contain s plus 2. So let's say that my s is now minus 2, so that I can kill the term s plus 2. So in that case it will be 1 equal to, all the other go to 0, and I have lambda 2 into minus 2 into minus 2 minus 1, that is minus 1, which implies that my lambda 2 is equal to 1 by 2. My lambda 2 comes out to be 1 by 2. Now in order to find the value of lambda 1, what I'll do is I'll compare the coefficients of s cube in LHS and RHS. So I'll compare coefficients of s cube in LHS and RHS. So if I do that, in LHS the coefficient is 0, then this will be equal to C1 from this term plus C2 from the second term plus lambda 1 from the third term. But now in the fourth term we don't have anything. So this I can simply write as equal to C1 value is minus 1, C, C2 is minus 1, C1 is 1 by 4 plus lambda 1, which means that my lambda 1 comes out to be 3 by 4. Okay, so what do I have is my C1 comes out to be 1 by 4, my C2 comes out to be minus 1, my lambda 1 comes out to be 3 by 4, and my lambda 2 is equal to 1 by 2, and my x of s is equal to C1 upon s, so that is equal to 1 by 4s plus C2 upon s plus 1, so that is minus 1 upon s plus 1 plus lambda 1 upon s plus 2, so this is equal to 3 by 4 times s plus 2 plus 1 by 2 times s plus 2 square. So this is the partial fraction based representation of my Laplace transform. Now we are having three cases. So the first case is of the ROC, which is given something like this, that is real part of s is greater than minus 1. So if we look at this case properly, it is something like this. I'm actually having, okay, let's say it is not minus 1, something. Yeah, I'll modify this question a bit, that is it is greater than 0 and it is something like this. Yeah, let's say my ROC is greater than 0. So I'm having a pole here at 0, a pole at minus 1 and a pole at minus 2, and my ROC is real part of s greater than 0, that is it is something like this. So this means that all of these signals or all of these components will be right hand sided, then only in that case my region of convergence will be intersection of ROC of this, which will be something like this, which would be something like this, and for this something like this, that is all of these components will be leading to a signal which is right hand sided. Now if we look at this table here, I am having a component which is something like this, 1 upon s plus a, and also my region of convergence is right hand sided, that is right to rightmost pole. So therefore here also, if I am having something like this, then the time domain representation will be leading to e power minus at u of t. So here my this 1 upon s plus 1 here, my a is equal to 1, and therefore I can use e power minus at u of t. But along with that, first I have this 1 upon s term. So this 1 upon s is simply my unit step signal. So this I can write as 1 by 4 ut. Then this minus this s1 upon s plus 1 will lead to e power minus t ut. This thing 3 by 4 s plus 2 is simply the same thing, but now my a value is 2, so it is 3 by 4 e power minus minus 2t u of t. Now let us consider this factor here, 1 upon s plus 2. So if I differentiate this 1 upon s plus 1 once, so if I differentiate this, so I'll get minus 1 upon s plus 1 square. So if I have t into e power minus t u of t, then this will have my Laplace transform minus of differentiation of Laplace transform of e power minus t ut, that is minus of this term here, that was, it will become plus 1 upon s plus 1 square. So using this I can write it as 1 by 2 e power minus 2t u of t. So this is the first case that we have. The second case that we are having is real part of s is less than minus 2. So what does it say? It's something like this. My minus 2 is here, my minus 1 is here, and it is 0. So my ROC is something like this. So I'll get this only when this 0 is also contributing in this direction and this 1 is also contributing in this direction, which means that all of my signals are left hand sided. So if I consider all of them as left hand sided, then this is the case that I am getting, that is this 1 upon s plus a will give me a term something like this, e power minus at u of minus t. So first of all here, this 1 upon 4s will lead me to u of minus t, so that will be equal to minus of 1 upon, or rather minus of u of minus t. 1 upon s plus 1 will give me minus times minus of e power minus t u of minus t. Then this 1 upon s plus 2 will lead to minus 3 by 4 e power minus 2t u of minus t. And this factor will again give me a left hand sided signal. So instead of u of t here, I'll be having minus of u of t. Minus 1 by 2 e power minus 2t with a t here. So I'm missing a factor of t here. Into u of minus t. Now let us consider the third case. So the third case that I'll consider is the case when my region of convergence is something like this. So if I draw it, it is, I'm having a 0 here, I'm having minus 1 here, and I'm having minus 2 here. If I draw lines here, then my region of convergence is something here. Which means that this 0 is contributing this way, that is leftwards, and this 1 is contributing in this direction, and this 2 is also contributing in this direction. That is, whatever is corresponding to minus 2, it is right hand sided. Whatever is corresponding to minus 1, it is right hand sided. And whatever is corresponding to 0, it is left hand sided. So I'll just copy this expression that I am having here. So I'm having 1 here, 1 here, and 1 here, and this will lead to left hand sided thing. So that therefore it will be 1 by 4 u of minus t. This corresponding to minus 1 is giving me a right hand sided thing, so it is simply e power minus t u of t. Similarly, this is giving me a right hand sided thing, so it is e power minus 2t u of t, plus this is equal to 1 by 2 into t times e power minus 2t u of t. So for all the three cases, my region of convergence comes something like this. Any doubts in this question? Okay. Let's move on to the next question. So here, what we are having is something like this. So I'm given a Laplace transform that is 1 upon s plus 1, s square plus s plus 1, and the region of convergence is given as real part of s greater than minus 1 by 2. So again, we'll first try to find the partial fractions for this. So this x of s is equal to 1 upon s plus 1, or let's say c1 upon s plus 1. Okay, let me write it properly. So this is equal to 1 upon s plus 1 into s square plus s plus 1, and this I can write as c1 upon s plus 1. Now this is a quadratic equation, and the partial fraction form for this is simply a linear polynomial or a linear equation on the numerator, that is c2s plus c3 upon s square plus s plus 1. Now I can again write this as c1 into s square plus s plus 1 plus s plus 1 multiplied by c2s plus c3 whole divided by s plus 1 into s square plus s plus 1. So this I can then simplify comparing these two. I can write it as 1 is equal to c1 into s square plus s plus 1 plus c1, so I'm missing a c1 factor here, c1 into, no, okay. So this is equal to s plus 1 multiplied by c2s plus c3. Now let us first try to find the value of this c1. So for that I'll do s equal to minus 1 and kill this term here. I'll try to make this second term 0. So this is equal to 1 equal to c1 into minus 1 square, that is 1 minus 1 plus 1, which implies that my c1 comes out to be 1. Now let us try to find the value of c2 and c3. Let's do c3 first. So for c3 we'll try to kill this c2 term, and since we have the value of c1 we can easily find substitute it and find the value of c3. So for that let us say I am having my s is equal to 0. So for this what I'll have is 1 equal to c1 into 1 plus 1 multiplied by c3, which means that my c1 comes out to be 1, c3, my c3 comes out to be 1 minus c1, which is equal to 1 minus 1, which is equal to 0. So my c3 is equal to 0. Now let us try to find out the value of c2, and for that I'll compare coefficients of s square. So if I do that, in LHS I have 0, which is equal to c1, which is coefficient for here, and here I have plus c2, which means that my c2 equal to minus c1, which implies that my c2 is equal to minus 1. Therefore x of s is equal to c1 upon s plus 1, that is 1 upon s plus 1 minus 1 upon s square plus s plus 1. So this is what I am having here, and now we need to find the inverse Laplace transform of this for the region of convergence given as this. So what we have is x of s is equal to 1 upon s plus 1 minus 1 upon s square plus s plus 1. Now consider this factor s square plus s plus 1 and let us try to complete its square. That is, let us try to get it in some quadratic form. So I can write it as s square plus 2 into 1 by 2 into s. So I want it something like this, a square plus 2ab plus b square. So here a is my s and b is 1 by 2. So I'll just add 1 by 2 square and subtract 1 by 2 square plus 1. So if I do that, this part here will lead to s plus 1 by 2 whole square. So this is equal to s plus 1 by 2 square, and this part is 1 minus 1 by 4. So this is 1 minus 1 by 4, which is equal to 3 by 4. So I am having 3 by 4 here. So I can substitute it here. So I can write it as 1 upon s plus 1 minus, I think I made some mistake. Yeah, my C2 comes out to be minus 1 and C3 is 0, so it will be having a factor of s here. Extremely sorry, this will have factor of s here. Yeah. So this comes out to be s upon s plus 1 by 2 square plus, I can write it as root 3 by 2 whole square. Now this we know, this we very well know, that inverse of this is simply e power minus t ut, and so why I am considering right hand sided thing, because I have a pole here which is at minus 1 and I have two poles at location some at minus 1 by 2 here, and this is plus root 3 by 2 and this is minus root 3 by 2, and I have been given the region of convergence which is greater than, whose real part is greater than minus 1 by 2, which is something like this, which means that 1 will also contribute in this direction only, which means this will also lead to a right hand sided signal, and this part will also lead to a right hand sided signal. So if that is the case, then I know the inverse Laplace transform of this factor, which is simply e power minus t u of t. This we very well know. Now let us try to find what is the Laplace transform of this part, inverse Laplace transform of this function which is here, that is this we know, and this we will now try to find. So I have this s upon s plus 1 by 2 whole square plus root 3 by 2 whole square, which I can write as s plus 1 by 2 upon s plus 1 by 2 whole square plus root 3 by 2 whole square minus, this is 1 by 2 here, upon the same term, that is s plus 1 by 2 square plus root 3 by 2 whole square. So let me multiply and divide the numerator by root 3. So what I'll have is root 3 by 2 into 1 by root 3. So what kind of thing I am having here? So let us go back here and look at these two functions, these two. So if I have s upon s square, s upon s square plus omega naught square then its inverse Laplace transform is cos of omega naught t u of t. And if I try to use this property, that is e power minus at x of t will have a Laplace transform of x of s plus a, that is shift in s domain property. So in that case, e power minus at cos of omega naught t ut will be having a Laplace transform of s plus a upon s plus a square plus omega naught square. Similarly, if I have a case, if I observe this here, and if I have e power minus at sine of omega naught t ut, then this will be having a Laplace transform of omega naught upon s plus a square plus omega naught square. And we are getting those two terms exactly in this format. But here my a is equal to 1 by 2 and my omega naught is equal to root 3 by 2. So in that case, this will be having a Laplace transform of e power minus t by 2 into cos of omega naught is root 3 by 2. So this is root 3 by 2 t ut, and minus we have 1 by root 3 here, and this will correspond to a sine. So if you observe here, it will correspond to a sine, and omega naught is root 3 by 2. So this will lead to e power minus t by 2 sine of root 3 by 2 t u of t. So therefore this entire thing that we are getting is something of this form. So the final thing that we are getting is x t is equal to e power minus t ut plus e power, or rather it is minus sign here, not plus, this minus sign we have, minus e power minus t by 2 cos of root 3 by 2 t ut plus 1 by root 3 e power minus t by 2 sine of root 3 by 2 t times u of t. So this is the value of x of t that we are getting here. Any questions for this? Any doubts in this question? Okay, let's go to the next part. So now we have this Laplace transform, and ROC is given as a real part of s greater than minus 2. Now I'll write this x of s something like this: 5 upon s plus 1 multiplied by s square plus s plus 1 plus e power minus 7s upon s plus 1 multiplied by s square plus s plus 1. Now this thing 1 upon s plus 1 into s square plus s plus 1 we have already found here. If we look at this question here, the previous question that we have looked at was exactly same: 1 upon s plus 1 s square plus s plus 1 with region of convergence are a real part of s greater than minus 1 by 2. We have found its inverse Laplace transform, which is something like this. So I'll just rewrite it here. So 1 upon s plus 1 s square plus s plus 1, this has an inverse Laplace transform as this we have obtained. So this, let's say, is x tilde t, and this x tilde t is equal to e power minus t ut minus e power minus t by 2 cos of root 3 by 2t plus 1 by root 3 e power minus t by 2 sine of root 3 by 2 t. This we have found out. And let's say this is my x tilde of s, which is equal to this, and the region of convergence was exactly this. So if I can write this using this x tilde of s, this is nothing but x 5 times x tilde of s plus e power minus 7s into x tilde of s. So this is what we are having here. And now if I take inverse Laplace transform, so if I try to find x of t, then using linearity property, this will be 5 times x tilde of t plus the Laplace transform of this factor here. Now again, if we look at time shift property, so looking at time shift property, what it says, if I shift any signal, let's say x hat of t by a factor x of t naught, and this x of t, let's say this initially I have a signal x hat of t and it has a Laplace transform as x hat of s, then if I shift this x hat of t by a factor of t naught, something like this, then the Laplace transform of this signal will be a shifted version, will be a scaled version, something like this, into x hat of s. Now if I compare these two, my x hat of s is simply my x tilde of s, and the value of t naught is equal to 7. So this is simply x tilde of t but shifted by a factor of 7. So this is what we are getting. So if I write it properly, it will be equal to 5 times e power minus t u of t minus e power minus t by 2 cos of root 3 by 2t plus 1 by root 3 e power minus t by 2 sine of root 3 by 2t plus e power minus t minus 7 u of t minus 7 minus e power minus t minus 7 by 2 cos of, okay, I'm missing the u of t factor here, ut u of t. So here I'll do this, that I just remove this u of t here and write it outside. Yeah, cos root 3 by 2 t minus 7 u of t minus 7 plus 1 by root 3 e power minus t minus 7 sine of root 3 by 2 t minus 7 multiplied by u of t minus 7. So this is the inverse Laplace transform of this signal. Any questions at this point? Okay. Let us look at the next question. So what we are given is, we need to find the transfer function of a series RLC circuit if input is a source voltage and output is the voltage across the capacitor. So what we are having is, let's say I am having an input voltage source, and this is simply my x of t equal to v of t, and it is an RLC circuit. So I am having a resistor R, I am having a capacitor C, or let's say I will draw an inductor here first, an inductor L, and a capacitor C, and the output is voltage across this capacitor, that is Vc of t, which is equal to, let's say, y of t, and we need to find the transfer function of this circuit which we are having here. Now let's say the current flowing through this circuit is I of t, and for capacitor, a current flowing through the capacitor, we have a relation that I of t equal to C times d dt of Vc of t. Since my Vc of t is y of t, I can write it as d dt of y of t. Now let's say the voltage across this inductor is VL of t, and the voltage across this resistor is VR of t. So in that case, my VR of t is simply R into IT from Ohm's law. So this comes out to be RC d dt of y of t, and if I consider the voltage across inductor, it is VL of t, it is simply L d dt of I of t. So this comes out to be equal to L into d dt of C into d dt of y of t. So this is equal to LC into d dt, or d2 by dt square of y of t. Now what we have from the KVL, that is voltage law. So the source voltage V of t, is equal to the voltage across resistor, that is VR of t, plus voltage across inductor, that is VL of t, plus voltage across capacitor, that is Vc of t, and this is equal to this VR of t we have obtained as RC d dt of y of t, d dt of y of t, plus this VL of t we have obtained as LC d2 by dt square y of t, and this Vc is equal to y of t, and this Vt is simply our input, that is x of t. So this x of t, I can write it just rearranging it, that is Lc d2 by dt square y of t plus Rc d dt of y of t plus y of t. Now we'll take the Laplace transform of this. We'll take Laplace transform, and I'm assuming that the initial conditions are 0. Laplace transform of this. So if I do that, then x of s is equal to Lc. Now if I have a signal y of t, and let's say its Laplace transform is y of s, then the Laplace transform of d dt of y of t will be equal to s into y of s. Similarly, if I again differentiate it, it will be, that is, if I do d2 by dt square of y of t, using the same property, this will be equal to s square times y of s. So this is Lc s square times y of s plus Rc s into y of s plus y of s. Okay, so I can write it as x of s is equal to, I can take out this y of s, and this I can write as LCS square plus RCS plus 1. Therefore, y of s upon x of s, which is my transfer function, that is h of s, it comes out to be 1 upon LCS square plus RCS plus 1. So this is the transfer function of this system that we have considered. Any question till this point? If not, let us consider the next question. So we are considering the same circuit here. We are considering this same circuit, but now what we need to find is, we need to find the value of the output y of t when my input is given as x of t, and my C takes value of 1, my resistor is 2, and my inductor L is 1. So these are some hypothetical values. So let us try to find y of t for the given setting. But for that, what we know is this h of s, the transfer function we have obtained is 1 upon s square LC plus s into RC plus 1, and if I substitute the value of R and L and C, it is simply 1 upon s square plus 2s plus 1, which is equal to 1 upon s plus 1 whole square. So this is what we have. Now this y of t is equal to x of t convolved with h of t. So one way is to find h of t using this h of s and then do the convolution operation, or what we can do is we can find first this y of s, which is x of s multiplied by h of s. We can find this and followed by an inverse Laplace transform. This is a more simpler way of finding it. So for that, what we'll do is we'll first try to find what is the value of x of s. So this x of t is given as something like this, u of t, and we know that the Laplace transform of u of t is simply 1 by s with a region of convergence of s greater than 0. So it is simply real part of s greater than 0, and this, since initial conditions were 0, it is a causal system, and therefore we have the ROC for this as real part of s greater than minus 1. Now this y of s is simply x of s multiplied by h of s. My x of s is 1 by s and my h of s is 1 upon s plus 1 square. So this is simply 1 upon s into s plus 1 square, and now we need to find its inverse Laplace transform, and for that we'll again use the partial fractions method, so that this can be written as c1 upon s plus c2 upon s plus 1 plus c3 upon s plus 1 square, which is equal to c1 into s plus 1 square plus c2 s into s plus 1 plus c3 s whole divided by s into s plus 1 square. So therefore what we have is, we have 1 is equal to c1 into s plus 1 square plus c2 into s plus 1 plus c3 into s. So let's say first we'll try to find the value of c1. So let's set s equal to 0 So in that case, my this equation reduces to c1 into 1 square, and rest terms go to 0, which means that c1 is equal to 1. The next thing that we'll find is the value of c3. So for that we'll substitute s equal to -1, and for that what we get is something like this. 1 equal to, this term goes to 0 and this also goes to 0, so minus of c3, which means that c3 equal to -1. And now we'll find the value of c2 by comparing. So we will compare coefficients of s square. So if I do that, on the LHS I have 0, here the coefficient is c1, plus here the coefficient is c2, which means that c2 equal to minus c1, which implies that my c2 is equal to -1. Therefore, if I use this expression for of y of s in terms of partial fractions, it comes out to be something like this. My y of s is equal to 1 upon s minus 1 upon s plus 1, that is my c2 value is -1, c1 value is 1, minus 1 upon s plus 1 square. And note that here, if I go back here, the region of convergence for this was real part of s greater than -1. Region of convergence for this was real part of s greater than 0, which means that the region of convergence of both of these will be simply intersection, which means that this will have region of convergence as real part of s greater than 0. That is something like this, which means that both -1 and 0, both of them will contribute towards right hand sided thing. That is, this y of s has a ROC that is right hand sided, which means that y of t will be right hand sided. And if I do that, if I take inverse Laplace transform, then this y of t will be equal to this part, this 1 by s will contribute to u of t. Then if I look at this part here, that is -1 upon s plus 1, so it will simply contribute to e power minus t ut, and we already have a minus sign here. And if I look at this part here, this will contribute to t into, so we know that t into e power minus t ut will be having a Laplace transform of 1 upon s plus 1 square. So this part here, 1 upon s plus 1 square, will contribute to this factor but with a minus sign. That is minus of t into e power minus t ut. Therefore, my yt is equal to 1 minus e power minus t into e power minus t u of. So this is my output. This is output of the system ht when my input x of t was unit step function. Any questions for this part? These are all the questions that I wanted to cover today. If you have questions or doubts in any part of today's session, please let me know. I'm happy to answer. If there are no questions, you people are free to leave the meeting. If you have any questions, please ask. Okay. If there are no further questions, thank you all for joining today's meeting, and you are free to leave the meeting. Thank you again.
Thank you, ma'am.
Thank you.